Hello and welcome to College Physics 1, Lecture 17, Weight, Apparent Weight, and Normal Force. In our previous several lectures, we've introduced forces, then looked at how to draw free body diagrams, and we started building from there. We began to work out equilibrium problems with Newton's second law, where there's no acceleration and our equations are set equal to zero. And then we built even further in our last lecture, where we talked about dynamics problems, that is, situations where acceleration has to be taken into account. Now, over the next several lectures, our goal is to reintroduce each individual force and describe them in a bit more detail, and often introduce a new equation, one for each of these forces. So let's begin with weight. The very first thing we want to understand before going into this is that mass and weight are not the same thing, even though these two terms are often interchanged in general conversation. To start, let's define each of them. Mass, by definition, is a quantity that's measured in kilograms, and it's something that describes an object's inertia, which is the tendency for an object to resist acceleration. And this should kind of make sense. This is kind of our physics-y way to define mass. Rather than just saying it's like the amount of stuff that something has, it's the tendency to resist being accelerated. So think about that. The higher mass you have, the harder it is to accelerate that object. So mass can be described in exactly that way, a resistance to acceleration. Further, note that mass is a scalar. It's just a number. There's no direction involved with mass. However, weight, which is measured in newtons, is a force. That is the gravitational force exerted by a planet or massive object. It could be another planet or the moon or something like that. But regardless, it's a force that's measured in newtons instead of kilograms for mass. Also note, as we've seen so far, weight is a vector, meaning it has direction. So this highlights a key difference between these two terms. Another great way to describe the two of these is to consider traveling to a different planet. So let's say you on Earth have a mass of 50 kilograms, in other words, a weight of 110 pounds. And then you traveled to Mars. Well, you still have a mass of 50 kilograms. You haven't changed how much material your body's made out of. But because Mars has a lower gravity, your weight would be lower on that planet, right? Because weight is a gravitational influence. This is also why, if you've ever seen footage of astronauts from the surface of the moon, when they walk, they kind of like bob back and forth. That's actually because their weight is so low on the moon due to its low gravity that it's much easier to walk, and so you kind of just bob back and forth as you do move along the surface. So they're not just being goofy. So this is a great way to highlight the difference between the two. Now, what's important though is to understand the actual relationship here. Even though they're not the same thing, they are related. And so our goal on this slide here is to introduce that relationship. How are they related? Well, to start, let's consider any object in freefall, in the image in the top right, that being an apple. Let's draw a free body diagram for the apple, or literally any object that's considered to be in freefall. From past discussions, any object in freefall is only under the influence of its weight force. There's no air resistance unless told otherwise, so we ignore it. There's no contact forces pushing or pulling on the object, so it's just weight pulling it downward. You can see the free body diagram for any object in freefall in the bottom right. Well, based on that free body diagram, we can write out Newton's laws. First, note that in the x direction, there are no forces. So when we write the sum of forces in the x direction, there are none, so it's just zero. In the y direction, we do have a force, and that's the weight. Note that we put a negative sign in front of the weight because it's pointing downward. And we set this equation equal to ma because there is acceleration in this direction by definition. So we have, for the sum of forces in the y direction, negative weight equals ma, where m is mass, a is the acceleration. But we already know what that acceleration is, ay. An object in free fall is under the influence of gravity. We know the acceleration due to gravity. It's negative 9.8 meters per second squared. In other words, minus g, where, again, g is 9.8. So our equation becomes negative w equals basically negative mg. Those negatives cancel out since there's one on either side, and thus we see our direct relationship between weight and mass. The weight of an object w is equal to the object's mass, m, times the acceleration due to gravity, g. And just a quick note that g is just the number 9.8 meters per second squared. There is no direction here. G is just a number, so you don't have to include a negative there. So this is a really good relationship. This is something that you'll see very commonly in the middle of math problems from here on out. So just understand that even though they're different, they are this closely related. Now, let's get into something a little bit weird. And that is our discussion on something called apparent weight. A very odd statement to make, and it's the first sentence you see on the screen. Gravity is not a force that you can feel or sense directly. The only reason you feel a weight or feel heavy is because of contact forces supporting you. That's a weird and kind of a mouthful kind of sentence, but think about what this is saying. Right now, presumably, you're sitting in a chair, or if not, just pretend you are. Well, there is a contact force supporting you in that chair, right? There's the normal force of the chair pushing up on you, holding you in place. But imagine then for just a second, just imagine that your chair, the floor, and everything underneath you, just absolutely everything underneath you disappears. You would start to fall. And while you're falling, you feel weightless. So that's what this statement is trying to say, that you only feel your weight because of something supporting you. So let's start defining something called an apparent weight. That is the weight that you feel. And we call this, or represent this with the symbol W for weight, and subscript APP for apparent. In other words, the apparent weight is equal to the magnitude of supporting contact forces. Right? So whatever is supporting you. Now, if you're in equilibrium, meaning if you're either at rest or if you're moving in a straight line and at a constant speed, those are both situations of equilibrium, you're going to weigh exactly, or you're going to feel exactly as heavy as you are. In other words, your weight will be the same as your apparent weight. But if you accelerate, that may not be the case. You can feel heavier or lighter than you actually are. A great example of this, I would argue, is when you are on a roller coaster. I'm sure most of us have been, maybe not all of us, especially if you're afraid of them, but just imagine, if you haven't been on one, imagine being on a roller coaster and you crest a hill. You're going over the top of a hill. Well, as you do that, you feel kind of lifted out of your seat. In fact, if it's a fast enough traversing of the hill, you can actually be lifted out of your seat. You feel much lighter than you actually are. Or imagine you're moving very fast in this roller coaster and now you're going through a big dip in the roller coaster, this big U shape in the roller coaster. Well, while doing that, you feel pushed and forced down into your seat. In other words, you feel heavier. So this is a great way to think about the difference between your actual weight and your apparent weight that you feel. Since not everyone has been on a roller coaster, I can assume all of us have at least been in an elevator. So let's use this example of an elevator to discuss this further. Well, Similarly, you're going to feel heavier when you're in an elevator that accelerates upward. So perhaps you get into the elevator, you hit a button for a higher floor, so the elevator has to accelerate from rest to start moving upward. Well, for that second or so that it's accelerating upward, you feel kind of pushed down against the floor a little bit harder. You feel heavier. So let's think about the forces acting on us while we are in this elevator. You're standing on the floor of the elevator. You have a weight associated with you, as does any object near the Earth's surface. That points downward. But there's also a normal force of the floor supporting you, pushing upward, perpendicular to the surface. One key note here is that because there is an upward acceleration, there is also an upward net force. So that means whatever force is pointing upward has to be larger, that being the normal force. And so we represent that by drawing a longer arrow for the normal force than we do for the weight. Again, because we're accelerating upward, so we must have a net force also pointing upward. So let's write out Newton's laws for such a situation. There are no forces in the x direction, so we ignore that. But we have forces in the y direction. We have the normal force upward, making it positive n, and the weight downward, or negative w. And there is acceleration, so we set this equal to ma. Now, I just choose to rearrange this equation here for n. So we have the same equation just rearranged. N is equal to w, the weight, plus m times a, the acceleration. So here's where I think, this is some personal bias because I'm a nerd, but I think something really beautiful is on display here. Remember that we said on the previous slide that your apparent weight is whatever is supporting you. And in the case of you standing in the elevator, it's the normal force that is supporting you, n. So we take the normal force, n, and replace it with our apparent weight. Because again, your apparent weight is whatever is supporting you, which is the normal force. So take this same equation and replace it with apparent weight. Thus, we see an amazing result. WAPP, or your apparent weight, in this case, is equal to the magnitude of supporting contact forces, which is your normal force. And so we write that equation again. I'm sort of repeating myself just there. Your apparent weight is equal to W, your true weight, plus something else. Right? We see WAPP equal to W, your true weight, plus that extra term. So that extra term is what's making you feel heavier than you actually are. And so it's based on your acceleration. So if you have a really big acceleration, you're going to add a huge term here and feel much heavier than you actually are. But if you're only very slightly accelerating, then you're only going to feel a little bit heavier than you actually are because this is a small term that you're adding on. And if there is no acceleration here, you're not accelerating at all, this term just goes to zero. And so your apparent weight is the same as your actual weight. You feel your normal weight. So this is such a good discussion to have. And I think it's really beautiful to see this kind of in a mathematical proof that you'll feel heavier in this situation. So this brings us to an example problem that we'll work out. This problem says the following. Anjay's mass is 70 kilograms. He is standing on a scale in an elevator that's moving at 5 meters per second. As the elevator slows to a stop, the scale reads 750 newtons. Before it stopped, when the elevator was was the elevator moving up or down? And we're going to ignore the second part of this question. I just want to focus on the conceptual part in the beginning. So we're going to ignore how long did it take the elevator to come to rest. We'll ignore this. So let's just focus on the concept. It wants to know if the elevator was moving upward or downward. Now, this is one of those questions that if a student got it, I think, and this isn't to discredit the student in any way. I think this is one where students have a really hard time grasping what to even do or look for. So let's just start with some basics. Let's focus on Andrzej's actual weight and Andrzej's apparent weight. Andrzej's actual weight is not given to us, but we can find it now. Recall that weight is equal to mass times the acceleration due to gravity. We are given Andrzej's mass, 70 kilograms, right? So we can find his weight. That would be 70 kilograms times the acceleration due to gravity, which is just, again, 9.8 meters per second squared. This is almost 70 times 10, so it should be just a bit less than that. We'll end up with about 686 newtons. So this is Andrzej's actual weight. But realize it says the scale is reading 750 newtons. Well, this is telling us his apparent weight, right? This what the scale is reading. So his apparent weight, WAPP, which, by the way, remember, is the magnitude of supporting contact forces. Well, it's the normal force that's supporting him. And that is told to be 750 newtons. So think about this conceptually first, right? Think about what's happening here. His apparent weight is greater than his actual weight. So let's draw a free body diagram and think about what's going on. In this case, it's just someone standing in an elevator again. So we have two forces acting on the person, that being Andrzej. There is his weight pointing downward. So we'll represent that with a W and an arrow pointing downward, and a normal force pointing upward. Well, think about what we just found. We said apparent weight is 750, that's the normal force. His actual weight, W, is 686. In other words, his normal force is bigger than his actual weight. So we're going to represent this with a longer arrow. Okay. Well, let's look at this conceptually. The normal force is larger. So that means we have a net upward force. I hope you can read this. I'll do my best. Upward force. Right? There's a net upward force because N is bigger than W. In other words, there is an upward acceleration. Right? So force and acceleration are proportional. So if the net force is upward, so is the acceleration. Well, we also know, based on the problem, that we are slowing down. Right? It says as it comes to a stop. So we know that we are slowing down, but with an upward or positive acceleration. So let's combine these two bits of information. Remember that by definition, if you're slowing down, acceleration points in the opposite direction of your motion. This is a rule we had in the past, so just try to remember this. If you're slowing down, acceleration points in the opposite direction of motion. If you're speeding up, it points in the same direction of motion. Well, we are slowing down, which means our acceleration and our direction of motion should be in opposite directions. So we'll say, I'll write this, motion is opposite, S-I-T-E, the acceleration. So if the acceleration is upward, then our motion is downward. And that is technically our answer. Right? The problem asks, was the elevator moving up or down? So again, let's just step through how we figured this out. We saw that we had an apparent weight of 750 newtons, that being the normal force, and an actual weight W of 686. Well, 750 is bigger than 686, so the normal force is greater than the weight, meaning there is a net upward force, hence an upward acceleration. But we're slowing down, so acceleration points in the opposite direction of motion, so if acceleration is upward, motion has to be downward. We can, in a way, kind of prove this with math. I'll run through this, but it's not severely important. So just note that on the side, I'm basically doing a mathematical proof of this. So let's set this up like any other problem we've worked out in the last few lectures, by writing out Newton's laws in the x and y direction. Note that there are no forces in the x direction, so you just set it equal to 0. But there are forces in the y direction, that's n minus w, and there is acceleration, so we set this equal to ma(y). Well, we want to figure out information about the acceleration in this problem, so let's solve for that. The acceleration is equal to, if you rearrange this equation a bit, you have n minus w divided by the mass. This will give you 750 newtons minus 686 newtons divided by the mass, which was 70 kilograms. Well, if you plug all this in, you'll get, and this is key, a positive 0.91 meters per second squared. And then we're back to where we started. If you didn't like conceptually that there was an upward acceleration in our description so far, now we have a proof that there's this upward acceleration. It's positive. And remember, something that's positive in the y direction is upward. So this is just us proving that we do indeed have an upward acceleration. So again, if you're slowing down, acceleration is going to point in the opposite direction of motion. So if we are accelerating upward, that means we have to be moving downward. Okay, so this is conceptually tricky for a lot of students. So just be careful with these concepts. I know it's not easy. So just kind of take some time to review it if that isn't perfectly okay with you at this point. So let's take this discussion of apparent weight just one step further and imagine that situation again where there was nothing supporting you. No chair, no floor, no ground, etc. Well, you'd experience something called free fall. So we'll say again, imagine someone in an elevator, unfortunately this time, that's in free fall, so no cable connected to it, it's just falling. Let's just say for the sake of the problem and, keeping things normal, the person survives, let's just say. So while the elevator is falling, well, the person inside is also falling at the exact same rate, right? They both start at 0 meters per second, but then they both fall at the same time, and so they're picking up speed at the same time. They're both falling together. So from the person's perspective inside, they're basically floating. They don't feel their weight at all. So this is the person experiencing what we call weightlessness. But be careful, again, that does not mean there's no weight, right? There is a weight that the person has because gravity is still acting on them. But they don't have the sensation of weight anymore because there's nothing supporting them. In other words, no normal force of the surface supporting them. So this weightlessness is felt anytime you are jumping through the air, falling down. In fact, sometimes it's sought after, like you can see on the right-hand side. There's even a plane that you can take up into high parts of the atmosphere, and it will do a very sudden maneuver where it's angled upward, and then it quickly turns over to angle back downward. And so the entire time that it's changing its direction, the people inside experience this concept of weightlessness, almost like they're out in space or on the, say, International Space Station. So it's just a really cool effect where you can experience this weightlessness. I think it's very expensive though, so I'm not sure normal people can afford that or if they even have the opportunity to do it, but it seems like a good time. Okay. This brings us to our final topic for today's lecture. We are talking about interactions with surfaces, so it only makes sense to talk about those surfaces, which brings us to the normal force. Any object that's on a surface is going to feel a force pushing back on it. So this force is always perpendicular to the surface, and it will always increase in strength if you are increasing the strength of what's pushing on the surface. In other words, it adjusts itself so that the forces always equal and opposite. So if you push down on your desk lightly, the normal force pushes back lightly. But if you keep pressing harder and harder, the normal force pushes back harder and harder. So just keep that in mind, that this force is always perpendicular to the surface, meaning straight off of the surface. It doesn't matter if that's your hand pushing into your table, so your table pushes back upward. Maybe you're using your hand to lean against a wall. The wall is going to push back outward. You could even push upward on your ceiling for some reason, and the ceiling pushes back down at you. So anytime you have an object on a surface, it experiences this normal force. Don't forget to tilt your axes if you're on an incline. The image at the bottom right shows you what happens when we set up our axes on an incline. Remember, the normal force always points straight off the surface, so it's going to be straight in the y direction off of the surface. But that introduces a complication. Your weight vector, which always points straight down, will no longer be on the y-axis because you've tilted it away from the vertical. So the angle between your y-axis and the weight vector is going to be the same angle as the incline that the object is on. And that's really hard for students to typically visualize, so I really quick tried to make a little animation of this. So just imagine you tilt your axes. Well, the area I've made in blue, you can see it's sweeping out that area in blue. So as you tilt your axes by some amount, the y-axis is swept out from below by some amount. So you can see that that angle down at the bottom, let me use my pen so you can see it. That angle down at the bottom here, shaped by this, ooh, that was really off, shaped by this triangle. Okay, I'm just scribbling on the page. Ignore that. So the point is, you sweep out the same area between the y-axis and your weight, down here, as you do with the incline. So these two angles are going to be the same. This will be true anytime you tilt your axes. So just be careful with that complication. Unfortunately, that does mean trig is brought into our problems very commonly for these type of situations. So let us conclude with one more example and then working out a few questions. This is example 1 for normal force discussion. It says that a skier slides down a slope at 27 degrees. On such a slope, which is steep, friction is basically negligible, so we're going to ignore friction in this case. The question asks, what is the skier's acceleration? So we start these problems the same way every single time. You start by drawing a free body diagram. So by doing this, we have to understand that we tilt our axes, so you can see that on the right, on the left. Our axes are tilted so that the x-axis points along the slope and the y-axis points straight off of the slope. Since friction is ignored, there are only two forces acting on the skier. The skier's weight pointing straight down and the normal force pointing straight off of the surface. And as we just discussed, the incline of the surface is some angle theta, so the angle between your y-axis and w is also theta. So this forms a little triangle where the weight has an x and a y component. Be careful with what you choose for your trig functions. The x direction, or the horizontal direction, is the opposite side of this angle. So the trig function that uses opposite and hypotenuse is sine. So this would be w sine theta. in the x direction. Whereas over here, this is the adjacent side along the y-axis, so the trig function that uses adjacent in hypotenuse is cosine. So this would be w cosine theta, right over here. So with this, we can now set up Newton's second law. I say this a lot, but remember, these problems all start the exact same way, by drawing a free body diagram and then writing out Newton's laws. So let's do this. Let's write out our sum of forces in the x and y direction. There is a force in the x direction in this case, and that is the x component of the weight, right? Right here we see w sine theta, the x component of the weight. That is the only force, though, w sine theta, in the x direction. In the y direction, we have two forces. The normal force pointing upward, so it's positive, and the weight pointing downward, or more specifically, the y component of the weight pointing downward, which is w cosine theta. At this point, we ask ourselves if the object is accelerating in either of these directions. The skier is indeed accelerating along the surface. There's a net force there, so we set this equal to ma. However, the skier should not be accelerating in the y direction, in other words, straight off or into the surface. So because there's no acceleration in the y direction, we can set that equation equal to 0. So, we've now set up our problem. We have our Newton's laws written out. It asks, what is the skier's acceleration? Well, we're solving for acceleration. So we're looking for this quantity here, ax. Well, that's the only place it shows up, which means we're going to have to use this equation to solve. So let's do that. We're going to use this equation to solve for the acceleration. I'm just going to write it again, so this is just redundant, but w sine theta equals max. So to solve for a, we would have to know everything else in this equation. We know the mass of the skier. We don't know the mass of the skier. And we also don't know the weight of the skier. But we do at least know the angle theta. But this seems like a big issue. We're solving for a, but we don't know two of the three terms in the equation. So here is a very difficult situation that arises every once in a while that confuses students. A lot of times you get to this point or an equation like this, and you don't know how to solve if you don't know the mass. Well, remember what we just introduced this lecture. We know that weight, the equation for weight, is m times g. So let's plug that in here. Instead of w, put mg. Right? Because weight is m times g. Well, now look at what happens. Just because of doing this, we have a mass on the left-hand side and a mass on the right-hand side. You can divide both sides by m, or the mass, and they cancel each other out. That's how you deal with a problem like this. We see the m's cancel out, thus leaving behind our expression for acceleration. Ax is equal to g sine theta. Now, for those of you who are keenly aware of everything that's been happening in my lectures, this equation should actually look very familiar to you. We actually gave this equation in an earlier lecture when we were solving motion on a ramp problems. We said the acceleration was plus or minus g sine theta. So we've technically just shown where that equation comes from, which I think, again, being nerdy and biased, is cool. Anyway, let's conclude. Let's solve this problem. We know g is 9.8 meters per second squared. And we know sine of theta, which is 27 degrees. Plugging all this in, we will find the skier's acceleration to be 4.4 meters per second squared. And there you have it. So again, just be careful of these tricks now that we know the equation for weight. Plug in mg. We don't have to worry about the mass in this problem then, and it makes things easy for us. So, again, let's conclude with a few questions. Question number 1. The box that you see is sitting on a floor of an elevator. The elevator is accelerating upward. What is the magnitude of the normal force on the box? Okay. Well, we're accelerating upward, which by definition means there must be a net upward force, meaning they will not be equal, and it can't be equal to 0 because it has to balance the weight force pulling this thing down. So we are either seeing that the normal force is bigger than, smaller than the weight, or there's not enough info. Well, I'll tell you, there is enough info. We know that there is a net upward force, which means the force that's pointing upward has to be larger. So when you draw a free body diagram of this, you have normal force pointing up, weight pointing down. So we know the normal force must be larger than the weight. Because we are accelerating upward, the upward force is bigger. Okay, let's try to use that same idea to solve question 2, which is commonly answered wrong. A box is being pulled to the right at a steady speed by a rope that angles upward. In this situation, what can we say about the normal force? All right, so this one often tricks students. It says at a steady speed, and so commonly students will choose option B. But that is not correct. That their reasoning is decent. I mean, because we learned that if something's moving at a steady speed, there should be no net force, and so the forces should be equal. That is still true, but there's more than one force pointing upward now. In the free body diagram we have for this, this is really small, we have a normal force pointing upward, the weight pointing downward, but there's also that tension slightly pointing upward as well. So the normal force and the tension together have to balance the weight. So it's those two together that balance the weight, meaning normal force is smaller than the weight because it has to be the normal force plus that extra to equal the weight. So the answer is actually C. The normal force is less than the weight because it's the normal force and the tension together that add up to get you the weight force. So, very tricky question. This brings us to question 3. A 50 kilogram student, in other words, a weight of 490 newtons, gets into a 1,000 kilogram elevator at rest and stands on a scale. The elevator then accelerates upward. What would the scale read? Okay. Well, in this case, we're accelerating upward, which we should know by now means there's a net upward force. If there's a net upward force, whichever force is pointing upward has to be larger. That would be the normal force, right? For the student standing on this scale, there's the normal force up and their weight down. Well, we know that because there's an upward acceleration, there's an upward net force, meaning the normal force is larger than the weight. Remember that normal force is what supports us, so that's our apparent weight. So our apparent weight, or the normal force, is bigger than our true weight, so we will see the scale read a larger value than our true weight. So again, the process of reasoning here, upward acceleration means an upward net force, which means the force pointing upward, the normal force, is larger. And we know that the normal force is what's supporting us, meaning that is our apparent weight, or what the scale would read. It's larger than the actual weight, so it's bigger than 490. And our final question for this lecture. Very similar situation, only this time the elevator cable breaks and the person and the elevator are now falling downward. What would the reading of the scale be in this case? And by the way, this is kind of a dark problem. I didn't write this one just for clarity, but you get the idea. All right, well, they're both in free fall. We actually had this discussion earlier in the lecture. The elevator and the person are falling at the exact same rate. As a result, there is no net force supporting the person anymore, right? There's no normal force supporting him anymore because he's falling down. Without anything supporting you, you don't have an apparent weight by definition. And so it's zero. The person will feel weightless. In other words, the scale would read 0 newtons. Kind of an interesting problem. So anything in free fall has a feeling of weightlessness. So no net force as a result. Okay, with this, we will conclude today's lecture. We will move on to talking about other forces like friction and drag in our future lectures. As always, thanks for watching and have a great day.